And here we go. Okay, so guys, today what we're going to do is we are going to have a deep conversation similar to the one that we had about ionic bonding, only we're going to have a similar conversation about covalent bonding. But before we do, we are going to wrap up our conversation about covalent or ionic bonding by talking about how ionically bonded substances behave on a macro scale, now that you understand the idea of lattices. So in just a minute, we're going to do ionic bonding and lattices for another moment or two. And then, guys, we are going to spend the rest of the day today talking about covalent bonding, which leads to molecules, of course. And then as we talk about molecules, we are going to do a really quick review of Lewis dot molecular structures with the idea that the only way to really do them is to practice them. And we will practice on them for one and get your questions answered, reconnect you with that, and then call it a day. You guys ready to go? Here we go. All right. So we are now going to, as I said, wrap up ionic bonding, and we are going to do this, guys, by way of comparison. So these are the things that you need to know, and it's just a laundry list. You may as well write them down. These are the things that you need to know about ionically bonded substances. Now, for this stuff to make sense, you should have a mental picture of an ionically bonded substance. I like to use table salt because it's familiar. So guys, these are the things that are all true of table salt. Number one, they tend to be solids. I have no idea why that is capitalized. Tend to be solids at room temperature. So they are solids at room temperature. Is that true of table salt? Absolutely. Number two, they are crystalline. What does that mean? Well, guys, when something is crystalline, it has flat surfaces and sharp edges. If you picture a grain of table salt, you know that it's somewhat cubic in structure with, again, flat surfaces and sharp edges. In addition, ionically bonded substances, salts, tend to be brittle. You hit them with hammers and they shatter. They do not deform. They are not malleable. In addition, when they break, they tend to leave smooth, flat surfaces. And then, guys, finally, they have ridiculously high melting points. If you don't believe me, go home, grab a saucepan, fill it up with table salt, and throw it on the stove. You're not going to get it to melt. Although it'd be fun to try. Yeah. I don't know. Let's see if Siri knows. What is the melting point of table salt? Come on, Siri. Oh, she's checking on that. Talk to me. So it looks like about 800 Celsius. And she converted it to Kelvin, and the number, yeah, that's right. So 1074 Kelvin. Yeah, so about 800 Celsius.
Sure, can you understand?
Try. Yeah, give it a shot. Okay. So guys, here's the $11,000 question that you've got to be able to answer. You all signed off on this and you agreed that all of these things are true. The question is, why is all of this true? Why is it true that salts, table salt as an example, are solids? They have high melting points, they're crystalline, they're brittle. Why are all of these things true? And the answer to that is a one-word answer. The lattice. That's it. Guys, every single one of these realities can be tracked back to the idea that table salt on an atomic level looks like this. So, why is it that these things tend to be solids at room temperature, which maps itself back to the fact that they have very high melting points? Why is that true? Looking at this. It's all the ionic bonds, right? Guys, this is not one sodium to one chlorine. It's the relationship times 6, that every chlorine is associated with 6 sodiums and every sodium is associated with 6 chlorines. And all of those rich, complex interactions, and I heard Everett say the lattice energy, exactly, that comes as a result, makes these things solids at room temperature because they have such high melting points. And again, it's that lattice association. Now guys, this one is cool. Why are they crystalline? Why do they have flat surfaces and why are they brittle? Well guys, the answer is this. Think about the lattice, and I'm just going to pull one off. Pretend like I didn't, but no, I don't want that one. I want one of these. Oh gosh. All right, so guys, the idea is this. The grays represent sodiums. So imagine that we've got this surface, and this is maybe kind of what like a crystal of salt looks like, of course, times a babillion, because there's babillions of atoms in there. But guys, what are the chances of a sodium just hanging on like this? It's not going to happen, right? Because that sodium is only associated with one chloride, and as a result, it's not very tightly bound, and those just tend to slough off. So all these little hanger-oners that we could potentially have sitting on the surface of the crystal don't tend to hang on very long because they're not very tightly bound and they fall off. So when those fall off, what are we left with? Flat surfaces and sharp edges. So guys, again, because of the richness of the associations necessary to hold these together, you end up with these sort of shearing along flat surfaces. Does that make sense? But now this is the one that's really cool to me. Why are they so brittle? Because this is neat. Let me put this back together and let's talk about it. So again, what is it that gives the lattice its strength? All the associations in the ionic bonds, right? So guys, let's look at this one plane at a time. So this chlorine is associated with this sodium. This sodium is associated with this chlorine. This chlorine is associated with this sodium. So guys, these always line up positive to negative. Positive to negative, positive to negative, positive to negative. And that repeats itself all the way through the crystal. You get the idea? Now, imagine that I hit this with a hammer. And if I can get this crystal to shift, ooh, I've never actually done this. But if I can get this crystal to shift, so it's like this, and if I can hit it and get it to shift this much, and how much is that? The width of one atom. If I can get this to shift one atom's width, what happened to the alignment of the charges? It's now negative to negative and positive to positive, and those don't attract. What do? They repel, and the crystal blows apart. You get it? That's why these things are brittle, is the very same attractions that make them so stable. If you can shift that one atom's width, those attractions become destructive repulsions, and the crystal blows apart, and that's what makes them brittle. You get the idea? Okay, so guys, let me pause for a minute, and anything that you need to write down in your notes, tracking these things back to the lattice, go ahead and do that. I don't know what you need to add, so I'll just give you a second while I put my salt back together. Yeah. So, yeah, and that's exactly why. So, guys, the question on the table is why are metals so malleable? And then the answer is that sea of electrons. The bonds that exist within metals are diffuse. It's a generic attraction between the nuclei to that sea of electrons, and because those bonds don't have specific locations, they're easier to shift because all you're doing is distorting the sea of electrons, and that's what makes them malleable. So, yeah, you can change that, of course. You can take metals and make them brittle, and you do that by adding different types of atoms. They call it doping and making alloys. And when you add different types of atoms in there, you can actually freeze some of those bonds, giving them location, but then that makes the metal brittle. So, yeah, and that's the thing that's really cool about metallurgy. Like making really, really nice knives, you can actually rearrange the structure of these things and freeze some of those atoms in place simply by how fast you cool the metal after you've shaped it. So it's really neat. It's fun. There's a Nova special on it that's really cool. So, you guys good on ionic bonding? Yeah.
So you said that like the actual salt would be a lot bigger than that?
Yeah.
Because there's like a ton of those?
Yeah.
So what stops it from like being huge? Because like table salt is just a bunch of little ones?
Not when you dig it out of the ground. No, when you dig salt out of the ground, it's in big old rocks. It doesn't look anything like comes out of your salt shaker. They grind it. Yeah, physically they grind. You can actually now, I think even at Harmon's, the wildly overpriced but really tasty grocery store, you can actually buy rocks of salt, and then you can put it in a grinder and grind them up. So it actually does come as big chunks, and then they grind it up. So, you guys good? We good? All right. So guys, in contrast, what about covalent bonds? Well guys, all of these things are true of covalently bonded structures. They can be solids, liquids, or gases at room temperature. They have low melting points. They tend to be very volatile, which you may remember means they vaporize easily. They tend to be ductile. That means you can stretch them out like taffy. And they tend to be malleable, which means smushable. Of course, there are some examples that aren't true of this, like graphite. That's certainly brittle. But in general, this tends to be true. So guys, again, the important question, oh, go ahead, Josh.
So then graphite's just carbon, right?
Graphite is just carbon.
So why is it that is?
Why? Yeah, and we're actually going to talk about it in a couple days. The answer is because carbon is what is called a covalent network solid. And what that means is that every carbon is, well, here. Every carbon is actually, this is what diamond looks like. Well, and this is what graphite looks like, but let's use diamond as an example. So the reason is because every carbon is covalently bonded to neighboring carbons. It almost kind of looks like a salt, right? Because you have a definite lattice structure. And this is all covalently bonded together, and that's what makes it behave more like an ion, like a crystal, than it does like a covalently bonded a molecule. And it's because of these covalent bonds that exist through the entire structure. And you'll find out in a couple days that's called a covalent network solid, and we're going to talk about them later. So guys, again, the big question is why? We understand that all of these things are true because of the ionically bonded network, the lattice. So guys, why are all of these things true? Why are covalently bonded substances, why do they have all of these properties? It's not because of the covalent bonds. Guys, why is this true? Why are all of these things true about covalently bonded substances? Say it again. They're I heard words. Yeah, keep going. It's because guys, it's because of their polarities, and you've got to understand this. When we think about a lattice, everything that we know to be true is because of the ionic bonds. So as these multiply themselves out to something like a salt crystal that we can touch and understand, it's just a magnifying of these ionic bonds. Now guys, that is not true of molecules. So if we look at a water molecule, what are the forces that hold the hydrogens to the oxygens? Covalent bonds. But that has nothing to do with the macro scale behavior of water. So what does? So what is it that determines how water behaves on a larger macro scale basis? And the answer is not the covalent bonds. The covalent bonds simply form the molecules. But what is it that determines how the covalently bonded molecules interact with each other? What are the purple sticks? Intermolecular forces. And guys, that's the answer to the question. When you're talking about a salt, it's the ionic bonds that determine the macro scale behaviors. In a covalently bonded substance, it's not the covalent bonds that determine the macro scale behavior, it's the intermolecular forces between the molecules. So the reason that all of these things are true is because it's IMFs and not covalent bonds that determine the large-scale behavior of these substances. And you know that intermolecular forces are weaker, therefore all of these things tend to be true. Do you get the idea? I'm going to pause and let you scratch that down, guys, because that is a critical point. The large-scale behavior of covalently bonded molecular substances is determined by IMFs and not by the covalent bonds. It's critical that you understand that. So if you need to talk about that, I'd love to go deeper on it, but it's a fundamental idea that you've got to get. What do you think? You guys okay? Yeah. Correct. Well, they're related, right? So the covalent bonds lead to the polarity, but the polarity leads to the intermolecular forces. So certainly they're not independent of each other, but the point is that, for example, in ice, the water molecules are not covalently bonded to each other. So the forces that determine the behavior of ice, for example, are not determined by the strength of the covalent bonds. They're determined by the polar nature of the molecules that leads to intermolecular forces. Does that make sense? You guys okay? You're good? All right. So guys, now we're going to move on and just talk about covalent bonds. So here we go. This is what we said last time. And nobody had a great answer for it. But if you remember, I sort of set up the problem with covalent bonding. So guys, now we're going to answer the question. How is it that covalent bonding works? You have taken on faith, certainly since last year, and maybe since 8th grade when you learned this in your physical science class, guys, that covalent bonds form by sharing electrons. And some of you had that moment of crisis where you found out, or at least you realized, that sharing electrons should not create attraction, it should create repulsion, because electrons don't attract, they repel each other. So, how do we resolve this seeming conflict that yes, covalent bonding is formed by the sharing of electrons, and yet electrons on their own actually repel each other? So guys, let's start to flesh this out first in words, and then I got a little video to share with you, and let's talk about how this works. So first of all, what has to be true in order for these things to share electrons? In order for an atom to share electrons, and maybe if you don't understand the question, try this. So this is oxygen, element number 8, 1s, 2s, 2p. This is the orbital filling diagram for oxygen. What is it about oxygen that allows it to form bonds? Go ahead. The empty spaces, right? So guys, it's those empty spaces that become the bonding sites that allow these things to form these bonds. So guys, the first thing that we've got to understand that we need these things to have these empty spaces in order to form bonds. If these are all full up, the noble gases, this is not going to happen. You get the idea? Is that okay? Okay, so I'm going to actually steal this from you for a minute. It'll be right back. But I want to change this because we're going to go this in a little different direction. So guys, the idea then is that these have got to have these empty spaces in order to be available for bonding. So we understand then that this is the case, that these things have got to have empty spaces in order to be able to share and form these bonds. You okay with that idea? Okay. So with that said then, we're getting closer to how it is that sharing can create bonds. Go ahead. What's that? We're going to get there in a minute. For now, we're just going to be comfortable with the idea that there's spaces. If you guys understand hybridization, what you're going to find out is that it is in fact not these p orbitals that provide the space for the bonds to form. The s's and the p's merge together first, and we end up with what in this case would be sp3 hybrid orbitals, and they still have the spaces. And it's still two spaces. And so we'll look at that in 2 days. But for now, we're just comfortable with the idea that there's spaces. So guys, if you're not comfortable completely with the idea, consider this then. If we add to this a hydrogen atom, like so, and then if we do another hydrogen atom, you get the idea. Let me move this down though. So if we do another hydrogen atom, and that's a 1s, and it looks like that, we get the idea that this can go in there, and that can go in there, and that forms the covalent bonds. Classic sharing of electrons. Go ahead.
So, question. I feel like this is should be just intuitive, like they're kind of confirmed. Do the electrons switch their band, or they become?
They do, yeah. So if they do happen to have similar spins, one of them will flip over. But that very point, Spencer, is getting us closer to why this happens. So guys, let's remind ourselves of a fundamental principle in the universe. Why does everything happen? Say it again. Not attraction. Why does anything happen in the universe, going back to chapters 5 and 19? Gives off energy. Entropy goes up, Gibbs free energy is released. A part of that is entropy, right? So guys, we know that water forms. Therefore, we know that it's got to be releasing energy, Gibbs free energy. So now, guys, we're ready to talk about fundamentally why does this work. So we know that sharing of electrons creates attraction. But now let's track this down. So first of all, why do these electrons want to go in these spaces? Why does that happen fundamentally? It releases energy, right? So we know that adding these electrons, sharing these electrons into these spaces causes a net release of energy. Are you okay with that idea? So when they come together, that creates a net release of energy. If you think about it, that then gives oxygen the electron structure of a noble gas. Those are stable. Stable means lower energy. It also fulfills the sort of like pseudo-octet rule for hydrogen. It doesn't have a P, so it just wants 2. But we know that we are filling up the oxygen. We're filling up the hydrogen. There's something about that makes it stable, that releases energy. You okay with why they pair up? But now here's the important question. Why does that create attraction? We understand that pairing happens because it releases energy. But why does that pairing create attraction? And guys, the answer is this. Let me show you the picture. This is the question. Why does this create attraction? And guys, the answer is contained in this picture. So here's the idea. We understand why they share. It releases energy. But why does sharing create attraction? And guys, the answer is it kind of doesn't. And yet it does. Here's the idea. So say that this is the nucleus of our oxygen, and say that this is the nucleus of one of our hydrogens. So this is oxygen, and this is hydrogen in our example. So what happens? Well, we share a pair of electrons. And again, why do they share into each other? It releases energy. But now, why does that create attraction? Because the answer is, in some ways it doesn't, because these electrons do in fact repel each other. There is still repulsion between those electrons. And there is also a repulsion between the nuclei of the hydrogen and the oxygen as they come together. So if that was the only game in town, this would not create attraction, it would create repulsion. So where, guys, is the attraction? Yes, the attraction, guys, is right here. This nucleus is attracted to this shared pair of electrons. And this nucleus is attracted to this shared pair of electrons. And these attractions overcome the repulsion between the electrons and the repulsion between the nuclei, and it creates a net attraction that we call a covalent bond. Now, guys, when we draw that like this, looking at all of the forces, the vectors of the forces, it's a little bit harder to see. So maybe consider this. When we go back to the idea that these electrons are like clouds. So here's the nucleus of one atom, here's the nucleus of the other atom. When those clouds overlap, guys, what? Oh, nuts. I know. This is happening more and more frequently now. All right, exit out of that. Go over here. Oh, poop. Go here. Click on this. Grab this. Go here. Do this and this and this and this. And grab this. So, guys, if you look over here at this picture, you can see this region right in here where we end up with this electron, because these are probabilities. We end up with this region in here where this pair of electrons creates a higher density. And these nuclei are attracted to this region of higher electron density, and that brings them together. And so, guys, this is an area that you need to know the name of. It is what is called a region of increased electron density. So if you want to scribble something that sort of looks like this, you need to understand that concept. That when covalent bonds form, initially there's a sharing of electrons. Why does that happen? Because we are completing octets. That completing of octets allows for a net release of energy, creating more stable structures. But that only explains the sharing. The attraction that comes as a result of sharing comes from this creation of a region of increased electron density to which both the nuclei are attracted, creating the covalent bond. Yeah? And that's exactly the point. Yeah, so the idea here is, you're right, Caleb, that if we're really just trying to complete octets, we'd be removing electrons. But understand that by definition, the elements that form these covalent bonds are the highly electronegative nonmetals. So when they come together, they are each strong enough that neither one of them will lose their electrons, so they end up sharing, which then does create this region of increased electron density. Yeah, you're absolutely right. So guys, do you now understand the answer to the sort of this seeming conundrum? That we understand that when we share electrons, it should create repulsion. The reason that it doesn't is because the sharing creates this region of increased electron density. Nuclei are attracted to that, and that's the net attraction that we call covalent bonding. Anything you want to explore there? You guys okay? You're good? Okay. So guys, if you're okay, let me give you another way to sort of visualize this, which is via this video. So here we go. Let me give this a little volume. This could be really loud. Let's see what happens. Oops. Yeah, well, it's actually being... There we go. Try this again. Coming back.
When two hydrogen atoms approach one another,
So here's what we've got. We've got the two hydrogen atoms right there. What do the clouds represent? The 1s orbital with one electron in each. But then, guys, you'll notice that they've given us a graphic representation of this. So the x-axis is the distance between the nuclei. So over here, the distance is great. And then this is the energy of the system. So down is low and high is up, higher energy. So here we go. How does this bond form?
When two hydrogen atoms approach one another, weak attractive forces operate between them. As they approach more closely, their 1s orbitals overlap more extensively.
So guys, notice that as their 1s orbitals overlap, energy is released. How do we know that energy is released? We see the energy curve drop. Now again, why is energy being released? Sort of, but why is energy being released? We're becoming stable, we're filling those 1s orbitals, right? Because when they're by themselves, each hydrogen has one electron in its 1s orbital. As they come together, now they're sharing, and they both now have that second electron as a result of sharing in their 1s orbital. That is a more stable structure, a lower energy structure. So they then reach that lower energy state.
And covalent bond formation occurs.
So guys, again now, we've got this space in between the nuclei. What do we call that? Region of increased electron density. Both nuclei are attracted to it. We get a covalent bond.
As the atoms move still closer...
Now guys, notice that they can actually do this. They can now come even closer together. And as they do, what happens to the energy? It goes up. That indicates that stress is being created. Where's the stress? The two nuclei now pushing on each other. We're now creating stress as the nuclei are too close and they're pushing on each other. So what are they going to do? Move back apart.
Together, the electron pair that forms the bond does not effectively screen the nuclei from one another, and nuclear repulsion becomes more important. The minimum energy structure in which the nuclei are separated by 0.74 angstroms corresponds to the best compromise between nuclear repulsions and the attractive interactions between the electrons and the two nuclei.
What do you?
When two electrons and...
So what do you think? You get the idea? This process of sharing and then mutual attraction and that resolution between repulsion and attraction, which then leads to bond length. Go ahead. Exactly. Yeah. I'm not even, all right, I'll mention it for a minute. So why does diatomic helium not exist? It's a noble gas, but there's actually another answer to it, because you can actually fudge the numbers and figure out a way that the diatomic helium could form, but what you find out is that the attraction doesn't overcome the repulsion and it blows apart. This all has to do with what is called molecular orbital theory. And thank goodness we don't have to teach it anymore. It used to be a part of the AP core, and so we would have to talk about not only why do some covalent bonds form, but why do other covalent bonds not form? And thankfully we don't have to do that anymore. But the answer to your question is, yeah, Jared, it's because the attraction overcomes the repulsion. You guys good? You get the idea with covalent bond formation? Okay. So guys, now what we're going to do, and this is sort of a foreshadowing to where we're headed. Wait, come back. Come on, there we go. It's a foreshadowing to where we're headed with this for the rest of the unit. Is, guys, we understand this idea from the beginning of our conversation that the fundamental behaviors of molecules, covalently bonded substances, the fundamental behavior of molecules has very little to do with the covalent bonds themselves. Of course, as Carson pointed out, there is a connection because the covalent bonding leads to polarity and polarity leads to intermolecular forces. But guys, to understand the way covalently bonded substances behave, the molecules, you've got to understand polarity and intermolecular forces. That's what we're going to do for the rest of this unit. It's all now going to be about polarity and intermolecular forces. And guys, I'm going to tell you right now, the AP authors love to nail you on this stuff. They can ask you one question on the AP test, and they can actually lay bare 4 to 5 to 6 different misunderstandings that you have by asking you one simple question like, why does sugar dissolve in water and alcohol doesn't? Actually, alcohol does too. Why does sugar dissolve in water and benzene doesn't? And by asking you that one question, they just had the opportunity to reveal 3 or 4 or 5 different things that you don't understand about covalent bonding, polarity, intermolecular forces, solubility, all these other things. So guys, bottom line is they're going to get you on this stuff. These are the questions that traditionally have the lowest mean scores on the AP test. They seem simple, and then you start to think about them and you're like, crap. So guys, we're going to spend days on this. So here's how we're going to start. First of all, this thing that we call the bonding continuum. Guys, I would encourage you not to write this stuff down. You know this stuff. I lifted these notes right out of, I just took last year's lecture over this stuff and I just put it in this lecture. This is all review. Just allow this to remind you. Guys, everything that we're going to do for the rest of the day except for the last thing is review. So let's review together. So guys, when we talk about the bonding continuum, we understand that on one end we have covalent bonding and on the other end we have ionic bonding. But guys, when we talk about covalent bonding, there's 2 types of covalent bonds. There's non-polar covalent bonds. And guys, what does it take to create a non-polar covalent bond? 2 of the same atoms, because they share perfectly. So anything other than the diatomics has to be a polar covalent bond. So let's talk about it. So guys, when we talk about ionic bonding, this is the idea that we have a highly electronegative nonmetal bonding to a low electronegativity metal. The nonmetal steals from the metal. The electron is transferred, in this case, to the chlorine. Everything we talked about last time. This then creates ions that attract. We get the lattice, that whole story. We should be good there. So then, guys, we talk about covalent bonding. And when we talk about nonpolar covalent bonding, we have a case where we have perfect sharing. In order for the electrons to be shared perfectly, again using our term, in order for this region of increased electron density to be completely symmetrical, the nuclei have got to have the same strength. And the only way that can be the case is if they're the same nuclei. So we have this negatively charged region in here, which is the shared electrons. And for those to be perfectly symmetrical, the nuclei have got to be the same so that they share perfectly. Remember that? Okay. So then, guys, what about all of the covalent bonds that are not the diatomics? Well, guys, in that case, we end up with something that looks like this. So the bonds that exist in water between hydrogen and oxygen. The oxygen is more electronegative than the hydrogen, but it's not strong enough to steal. In that case, as you can see from the shading, the electrons are shifted towards the oxygen, but not so much that we think of it as being ionic. And what does that create? Well, guys, that creates what we call dipoles. And you may remember that the more electronegative element is the negative end of the dipole, and the less electronegative element is the positive end of the dipole. And if we then come along and if we put another hydrogen nuclei up there, we end up with this, and this is shifted more in that direction. No, it's actually shifted in the other direction. That makes this cloud more, the increased electron density more shifted in this direction, making this dipole negative and making this end dipole positive for the entire molecule. Do you remember the idea? That the idea is that these electrons are shifting in this direction, these electrons are shifting in this direction, so the net shift is this way, and we end up with polar molecules and therefore intermolecular forces. Remember all of that stuff? Go ahead.
It's based on probability, right? It's just like on average, the electrons are going to be more, closer to the oxygen.
Absolutely, yes.
So then, when
So you might say that in any given instant, this could be here and this could be over here, right? And absolutely, you just hit right, and you got it in the ear? No? It was close. Okay, yeah. So the answer is yes. But so guys, what you're talking about is what we are going to give a name in a couple days. It's called an instantaneous dipole. And so, guys, what Carson is saying is, because these clouds represent probabilities and averages, wouldn't there be the probability in any given moment that the electron cloud is actually shifted towards the hydrogen in either direction? And the answer is absolutely. But because the term probability is a broad average, we know that on average these electrons are going to spend more of their time here. And we know that on average these electrons are going to spend more of their time there. And consequently, the overall trend holds. But you are correct that at any given instant, the electron cloud could be shifted in this direction, but in the next instant, it would go back, and the majority of the time it follows the trend of probability, so we don't have to deal with it as an exception. Do you know what I'm saying? Here's where it becomes a problem. Take, for example, this. You're talking about this idea of probability, right? What about nonpolar covalent bonding? We think about this as if this increased electron density is perfectly centered. But because these are probabilities, in any given moment, it could be this way. And if that is in fact the case, that makes this side slightly negative, and that makes this side slightly positive. We call this what is called an instantaneous dipole, and it actually explains why is it that hydrogen can be liquefied. Because if hydrogen is perfectly nonpolar, it should be a gas at any temperature. But because of this phenomenon of instantaneous dipoles, it is possible to liquefy hydrogen, because if we get them close enough, these very weak dipoles that are simply the result of probability do become strong enough to liquefy even hydrogen and helium. And we're going to talk more about that in a couple days. Okay, yeah? No. I mean, maybe on a very, very small scale, but not enough that we think about it that way. We think about volatility differently. We'll talk about it quickly. So the idea is this: if you've got a cup of water, we know how fast the molecules are moving from their temperature, but that's an average temperature. Some of them are moving much faster and some of them are moving much slower than the average, thus the average. And the ones that are moving faster, if they come to the surface, can escape. Not because their polarity instantaneously turns off, but because the ones that are moving faster, if they come to the surface, will leave. Yeah, okay. So guys, you okay with this idea of ionic covalent and polar and nonpolar covalent? Anything you want to explore there? We're going to talk more then about molecular polarities coming up. What we need to do now, and this is how we're going to end the day, is we need to remind ourselves about Lewis dot structures. Now guys, you got really, really proficient at these last year. So what I'd like to do is I'd like to offer you this. So guys, when we draw Lewis dot structures, allow me to remind you about some of the important things that we learned to do when we drew Lewis dot structures. And so it goes like this. When we drew Lewis dot structures, these are some of the things that we leveraged. We said the central atom tends to be the one with most bonding sites. We said that many times the chemical formulas are written in the orders that the atoms bond. Many times with these more complex molecules, they are written as a central atom, what's bonded to it, a central atom, and what's bonded to it. And guys, when you do Lewis dot structures, typically what you will do is get everything on the paper, single bond everything together, count up the total number of valence electrons, and then spread whatever valence electrons are left around the molecule until you complete octets. Do you remember all of that? And guys, when you're spreading those electrons around, there were two tricky bits. How many electrons can you put on hydrogen? Only 2, and then it's done. And guys, where do you have to put the electrons first when you're spreading the rest of the electrons around? On the halogens. Why on the halogens? They only have one bonding site, so they can only form one covalent bond. So in order for the halogens to get an octet, they've got to have 6 unbonded electrons. You guys remember all of that stuff? Okay, so what I'd like to do is I'd like to give you the opportunity to practice on one. So guys, in your notes, please do the Lewis dot structure for CO2, carbon dioxide. We'll use this as sort of our memory experience to make sure that we really do remember how to do these. Did you get it? Need another second? And guys, I'm going to go through this painfully slowly just to make sure we're catching all the important tricks. You guys good? Okay, so guys, here we go. I'm going to just switch to a blank screen, and I'm going to do this with you. So when we look at carbon dioxide, we are talking about, wow, CO2. Okay, so first thing we've got to do is figure out which atom is in the middle, which one is in the middle. It's got 4 bonding sites. Oxygen only has 2. It's written first, make them symmetrical, so on and so forth. So we're going to go oxygen and carbon and oxygen, and we put everything on the paper single bonded together. Now what we do is we count valence electrons. How many valence electrons does carbon have? Yeah, not 6, it's 4. It's the valence electrons. So this would be 4. Oxygen has 6. For a total of 12, 12, 12, and we add those up and we get 16 valence electrons. Now guys, how many do we already have on the board? We have 4, so we have 4 valence electrons. Good heavens, 4 valence electrons already on the board, so that leaves us a remainder of 12. Now, what are we going to do to get all of these electrons on the paper? And it doesn't really matter. You can spread them out however you want. You just need to get them all on the paper. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So now I've got those 12 electrons on the paper. And now, guys, we need to check the octet rule. Is this oxygen happy? Got a full octet. Is this carbon happy? Full octet. Is this oxygen happy? It is not. It's only got 4 valence electrons. So this is where we then start to push electrons around. We'll pull these off. We'll move these. Oops. All right. We'll pull those off. We'll move these over. Now we're getting closer. This oxygen's now got 6. Then, guys, we need to still complete octets, so we'll pull that over and we'll do that. And now we've created full octets where this oxygen has got 6 or 8 and carbon's got 8 and oxygen's got 8. They all now have full octets, and this would be carbon dioxide. You good? What's that? That's okay. So oxygen or carbon dioxide. Is good? Go ahead.
So why doesn't a double bond form between the two carbons and oxygens and then the other?
Well, if you formed a double bond here, you'd have 5 on 5. You'd have 10 electrons on carbon.
Well,
Why
the
does
two
it have two double bonds?
Oh, wait, what? So,
not three.
oh, so you're saying something like this? Okay, but hold on. If you do that, you can't put any more electrons on carbon, right? So what are you telling me to do? So 1, 2, like that? And then here, does that work? Hold on. So 2, 4, 6, 8, 10, 12, 14, 16. So we've got, oh, so that one works too. So guys, if both of those work, which one's right? Here's the thing you're not going to like. Neither of these is correct. You guys throughout the year are coming to get comfortable with the idea that there are very few always and nevers in this class. So guys, we are going to talk about which one of these is correct. But we're not going to call it correct because guys, both of these are possible. They both fulfill the octet rule. They both give us complete octets of 8 electrons. They both result in 16 total valence electrons. They are both possible. So what we are not going to talk about is which one is correct. We are going to talk about which one is favored. And so we need to talk about this. Now guys, here's the thing. You may remember last year. Some of you remember last year. Guys, you may remember last year, and I had you do something like this. I had you do the Lewis dot structure for sulfate. Any of you remember that from last year? And we did this on that lab where we had the model kits. And some of you even came to me and you did this for sulfate, minus the valence electrons, but it works. You can come up with a completely viable structure for sulfate that looks like this. But I marked it wrong, because that is not what sulfate does. Sulfate is tetrahedral, and it looks like this. And I know I had this conversation with a couple of you because I remember it from last year. And you came to me and you showed me this. And actually, I didn't mark it wrong. You came and showed me your lab, and I said, that's not sulfate. But guys, you came to me and you said, hey, this is sulfate. And I said, no, it's not. It actually looks like this. And you asked me, why isn't this right if it works? And do you remember my answer to you? Because it's not symmetrical. Do you remember? And we talked about the idea that the symmetry is higher in this than it is in this. And frankly, guys, I took the low road and I told you that this is not correct and that is because this is more symmetrical. Guys, it turns out that it is not a question of symmetry. This one is favored over this, but it is not a question of symmetry. So what is it? Well, guys, if we go back and look at our carbon dioxide example, you could also say that this is more symmetrical than that, right? But guys, it's not a question of symmetry. It is a question of what is called formal charge. This is the next thing in your notes. You may as well write it down. It is a question of what is called formal charge. Now guys, let me give you a really quick and dirty definition of formal charge. Formal charge is a measure of change during bonding. Formal charge is a measure of change during bonding. So guys, let me give you an analogy for what this means. Because I don't know if you've ever had this experience. You're probably too young, and this sounds horrible. And let me just tell you right now, my parents are divorced. Okay? With that said, I've had friends throughout the years that have gotten married, and frankly, and this sounds horrible, but you've sat there at their wedding, and I know that for many of you, you didn't even know this was possible, because where I'm from, we go to weddings where people come and it's not a temple event. But so you're sitting here at the wedding and the preacher is, hey, do you take this woman to be your lawfully wedded? Anyway, and so you're sitting there in the wedding and you see the husband, the groom and the bride and the groom, and they're facing one another, and you're just sitting there during the wedding going, I give him a year. This is not going to last. Seriously, and it sounds horrible. But guys, it really happens. But why does it happen? And guys, I would propose to you that the reason that some marriages are not going to last is because we are inherently selfish people, and it just requires too much change. Guys, don't go into getting engaged thinking, hey, they're going to change and this is going to work, because they're not and it isn't. So guys, the idea is this. You can identify relationships that are going to work because they're two people that were walking the same path, and they just happened to come together and walk the same path together. They're already headed in the same direction. So they're both into the same things. They're both into the same there's just a commonality about them that if they're both going in this direction, if they come together, it doesn't involve a whole lot of change, because if they never came together, they'd both end up being the same people necessary to come together. Well, but then you've got the other side of this where you've got biker guy and Molly Mormon chick, right? And Molly Mormon chick meets biker guy and they do the missionary dating thing, and biker guy's like, all right, I'm not going to the bars anymore. I get it. I'll go to church with you, and it lasts about a year and it blows up. Guys, the reason is because either biker guy is going to have to become like the girl, or the girl's going to have to start hanging out in the biker bars, because really fundamentally they haven't changed, and it's just too much stress and it's not going to last. Guys, the same thing is true of atoms. Atoms fundamentally don't want to change when they bond. And if they do have to change to bond, it creates stress. And that stress makes it less likely for the bond to form. Do you understand the analogy? So now the question is this. When you're sitting there at the wedding watching Molly Mormon girl and biker guy, you can look. You can see the stress. The pastor's going, this isn't going to work. But you can just feel it. But guys, how do we measure stress when it comes to atoms? And the answer is this. We can quantify change. So how do we quantify change when it comes to atoms? And guys, the answer is this. Again, it's through the concept of what we call formal charge. So guys, don't write any of this down until we get to the bottom. So how do we calculate formal charge? Well guys, it goes like this. When we do formal charge, it's a comparison. It's a before and after snapshot of the marriage. So here's how you do it. Each unbonded electron counts as one. Each bonded electron pair counts as one, and then this is the equation. Write this down. Formal charge is the unbonded score minus the bonded score. That's formal charge. It's the unbonded score. That's the picture before. What do they look like before? And then the bonded score. What do they look like after? And guys, the closer the before and after snapshot are, the more stable marriage, if you will. So again, unbonded electrons count as one, bonds count as one, and then it's unbonded minus bonded. So guys, let's do this. Let's go back to our carbon dioxide molecules. And let's figure out the formal charges on these atoms. So guys, it's unbonded minus bonded. So if you want a second to scratch these down really quick, I'll give you a moment to write them down. This is what you need to learn how to do. So here's how this goes. The first thing that we need to know is the unbonded score. So, hey, thank you. So the unbonded score. Guys, how many valence electrons does oxygen have? 6. How many valence electrons does carbon have? 4. So the unbonded score for oxygen is always 6. The unbonded score for carbon is always 4. The unbonded score for oxygen is always 6. Oxygen is 6. Carbon is 4. Oxygen is 6. Now we need the bonded scores. So what is the bonded score for this oxygen? Remember, each unbonded electron counts as 1, and each bond counts as 1. So it's 1, 2, 3, 4, 5. Minus 5 equals 1. Now, guys, let's do the carbon. 1, 2, 3, 4. So 4 minus 4 is equal to 0. Now let's do this oxygen. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1. Now we have figured out the formal charges on the individual atoms in that molecule. Now let's do that for the other molecule. This oxygen is 1, 2, 3, 4, 5, 6. Minus 6 equals 0. The carbon is 1, 2, 3, 4. Minus 4 equals 0. This oxygen is 1, 2, 3, 4, 5, 6. Minus 6 is equal to 0. Now we know the formal charges of all the atoms. Now, guys, this is important. You need to be able to communicate which one of these molecules is favored. So, given the calculations that you just did, which of these molecules is going to be favored? The one on the right or the one on the left? The one on the right. But how do you communicate that? And guys, this is not how to do it. You would not say the structure on the right is favored because the formal charge is 0. That is not true. What do these formal charges add up to? 0. What do these formal charges add up to? Also 0. So guys, let's talk about this really quick. What if they both didn't add up to 0? Your Lewis dot structure is wrong. So guys, this is an error check when you're doing Lewis dot structures. If your Lewis dot structures don't add up to 0, you've done it wrong. It's not just not favored, it's incorrect. With one exception. Say that we were doing this again for SO4 minus 2, or SO4. If we were doing this for sulfate, guess what the formal charges would add up to? Negative 2. So guys, the bottom line is the formal charges will always add up to the charge of the ion. If it's a neutral molecule, it'll add up to 0. So, with that said, it is not okay, and guys, you're going to get this wrong on the test. It is not okay to say the structure on the right is favored because the formal charge is 0. It's 0 in both cases. So how do we explain that this one is correct? You ready? Here's how we do it. The structure on the right is favored because the formal charges on the atoms are reduced. Do you see the distinction? It's not the formal charge on the molecule, it's the formal charges on the atoms. And the formal charges on the atoms in the right-hand structure are reduced. So here's the two important points. Talk about the formal charges of the atoms and not the molecule. Molecules do not have formal charges. The individual atoms do. And then the trick is the one that's favored is the one where the formal charges are reduced. Do you get the idea? Yeah. Okay, so the structure on the right is favored because the formal charges on the atoms are reduced. Again, the important points are on the atoms, not the molecule, but on the atoms, and that they are reduced. Not that they're 0, but that they are reduced. Yeah?
So reduced, you don't just put K less.
They're lower in magnitude, yeah. So if we could do a structure where, oh gosh, never mind, don't do that. But if we could do a structure where this was like a 2 and a negative 2, then this would be the one that's favored because it's reduced. It's lower in magnitude. So understand that they still have to add up to 0 or something's fundamentally wrong. But it's the one where the magnitude of the formal charges is lower. That's the one that's preferred or favored. That's what we mean. Yeah. You guys good? You okay? Formal charges? All right. So guys, we are all done. So let's go like this, and let's go like this. And here is your homework. We will grade this on Thursday. While you are writing this down, let's talk about pride. Zach, you're staying. Josh, Bus, you're staying. Eliza's staying. Josh's are staying. Shelby's not here. Hunter, you're staying. Vanessa, you are staying. Carson, you are staying. Alex, you are actually leaving because of this. Spencer Miller, you're staying. Parker, you're staying. McKay, you are staying. Man, we're going to have a party. And that's it. In addition to that, guys, if you ain't taken the last test, you need to come and talk with me during Pride. You're good. You're free. Okay, so guys, let me shut this off.